In the next few videos, I want to go through some of the limiting cases of the amplitude response of second-order systems. In particular, this system that we've seen with the resistor, inductor and capacitor in series, and the output taken across the capacitor. We'll start with the case of very small Q factors. As we've seen before, you can estimate the amplitude response in this case quite accurately by just extending the low frequency asymptote and the high frequency asymptote to the point where they meet. Oops, that's not a very good drawing because they meet at the resonant frequency. Then determining the gain at the resonant frequency by equating it to the Q factor. Drawing a line of gradient 20 dBs per decade through that point. Where it crosses this low frequency asymptote must be the lower frequency breakpoint of the pole. And where it crosses the high frequency asymptote is the higher frequency breakpoint of a pole. Not a brilliant diagram, but hopefully you get the idea. Well, it is often useful to be able to calculate exactly where these pole break frequencies are. And you can do that from the resonant frequency and the Q factor. Not by solving the full quadratic equation, although that would work, but by using a much simpler approximate expression. Now, you can determine the poles in terms of the resonant frequency and the Q factor by noting that the poles are the values of j omega for which this expression must be 0. In other words, they are the roots of this quadratic. So, my two poles must be given by the quadratic formula, which is minus b, in this case 1 over q omega naught, plus or minus the square root of b squared, that's 1 over q omega naught all squared, minus 4 times a, 1 over omega naught squared, times c, 1, all over 2a, all over 2 omega naught squared. That's a bit of an unwieldy expression, so I will multiply up everything by omega naught and see if I can simplify it a bit. If we multiply top and bottom by omega naught squared, that would give me minus omega naught over q plus or minus the square root of omega naught over q all squared minus 4 omega naught squared all over 2. I can extract the factor of omega naught squared out of this square root and write this as minus omega naught over 2q plus or minus the square root, well, omega naught times the square root of 1 over q squared minus 4 over 2, and extract the q from this square root here and end up with omega naught over 2q plus or minus the square root of omega naught over 2q times the square root of 1 minus 4 q squared. Now, if q is a very, very small number, then 4q squared is going to be much smaller than 1. So I could, to work out my first estimate of my pole, say, right, let's consider the first pole where this minus sign is taken here. P0. Minus omega naught over 2q minus omega naught over 2q times square root of 1 minus 4q squared. But if q squared is very small, then 4q squared will be much smaller than 1. I can neglect this term in comparison to the 1, and I would just end up with minus 2 omega naught over 2q, which is minus omega naught over q. That's my first pole. The other pole would come from taking the plus term here. Omega naught over 2q plus omega naught over 2q. Now, I can't just do the same approximation as I did before here, because these terms would end up cancelling out and I'd just be left with 0, which isn't a particularly good approximation for my other lower frequency pole. It's much better just to go and use that other result, that the product of the two poles is the square of the resonant frequency. And therefore, our other pole would be approximately omega naught squared divided by the pole that we've just worked out, minus omega naught squared over q. And that is minus omega naught times q. Oops. So we've got approximate expressions for our two poles. One of them is approximately at minus omega naught over q, and the other one is approximately at minus omega naught times q. Much easier. And they are much easier expressions to use if you want to know the poles of a second order system with a very small q factor. In terms of what it looks like, this is the amplitude response of a second order system with a very low q factor. You'll see that in this case the q factor is 0.1. The resonant frequency is 10 kilohertz. If I extended this high frequency asymptote up, it would hit there, go through 0 dBs at 10 kilohertz. The two pole break frequencies are at approximately 10 kilohertz times 0.1, or 1 kilohertz, and 10 kilohertz divided by 0.1, or 100 kilohertz. The phase response looks like this. Remember, the phase response of a single pole is approximated by going down through 45 degrees at the break frequency and arriving at minus 90 degrees at about 10 times the break frequency. So we've got this curve caused by the first pole here, and this further drop by 90 degrees down to minus 180 degrees caused by the second pole here. Those are the important results for very small q factors. Next time we'll have a look at the special case of q equals a half.